Здравей, Христо.
Здравей.
Радваме се да те видим на конференцията ни.
Твоята лекция... радвам да съм тук.
Да, твоята лекция ще бъде на английски, доколкото разбрах.
Но аз само искам да поясня, че освен, че ще е на английски, много от нещата са доста, така да кажем, визуални и с термини типични за като цяло индустрията, така че едва ли ще е толкова трудно да се разбира, ако някой не му е толкова силен английския. Същевременно, в последствие няма никакъв проблем да си поговорим и на български, когато стигнат до въпросите, ако има въпроси специфично на български, така че целта е общо взето възможно най-много хора да имат възможност да се докоснат до темата, ако им е интересно.
Разбира се, аз не мисля, че в тази сфера има някой, който да не може да се оправи с английски, до толкова, че да разбере идеята на лекцията. Темата, да кажем, Applications of Machine Learning in Modern Computer Graphics. И няколко думи за теб. Ти си, аз не се опитвам да превеждам този термин, защото не знам на български как ще звучи, но инженеринг менеджер с голям опит във всички основни етапи от софтуерната разработка. Участвал си в продукт или project management, в UI, UX дизайн, full stack development, DevOps, тестване и поддръжка. Доколкото знам, за теб е удоволствие да създаваш, да ръководиш, да подобряваш екипи, високопроизводителни екипи, които съответно се занимават и с доста сложни технически предизвикателства. Освен това, любимите теми са Web, Game Development и разбира се компютърна графика, както разбираме и от темата на лекцията. Аз искам да обърна едно внимание на нашите, не знам как се нарича в този формат на водена конференция, дали са зрители, дали са участници, но на хората, които присъстват тук на конференцията, че ако забелязват хората, които са поканени да изнесат лекции тук, обикновено с много голям опит и според мен е супер ценно и хубав момент да ги хванете за ушите, дето се казва, да ги заведете в някъде, било в отделна сесия, било да го притиснете в някой щанд, в случая щанда на Келс и да измъкнете от него всякаква любопитна и подробна информация, която бихте могли да извадите от един човек с толкова много опит. Христо, заповядай на сцената, е твоя и очакваме с интерес твоята презентация.
Thanks. I'll switch to English since this is the official announced language of the presentation. Thanks a lot for the introduction. I'm really glad to be here, and as you mentioned, basically I've been involved in various positions in software development over the last 16 years, both as engineering manager and as engineer. I'm really passionate about all things related to computer graphics. Currently, I'm software development manager at Chaos. I hope that you all know Chaos, but in case you don't, we are basically one of the world-leading companies when it comes to computer graphics. And it was really great to be awarded the Emmy Award just recently for engineering achievements. And you can see just few of the awesome TV series that are using our software to create really spectacular computer graphics. If you want to learn more about Chaos, you can visit our site. We have a ton of information there about job openings and what are we doing. So I encourage you to visit it. Okay, so let's get started with the lecture itself. Quick agenda. Basically, very quickly, we'll go through the evolution of AI, just so that we know what are its main challenges and what is future direction. By the way, this lecture doesn't assume any previous knowledge of deep learning or computer graphics, so we'll very briefly go over the most important things. Then we'll delve right into the actual applications of machine learning and deep learning in modern computer graphics. We'll see different examples of both improving the quality of generated images and generating new ones. And at the very end, we'll finish with a very interesting topic of the asterisk verse, as I've put it here, which is all the different metaverses, omniverses, and other virtual worlds that are quite viral over the last few months. And more importantly, what is their importance for machine learning. So let's start with a quick introduction to AI. Basically, deep learning in a nutshell, it is pretty much based, or at least conceptually, on the idea of the neuron in the human brain. And on that is built the so-called artificial neuron. That's pretty much a small, you could think about it as a small processing units that basically takes input, and it can have weights assigned to that input. It calculates that, applies some kind of activation function. This is something that is needed so that there's nonlinear output of that data. And basically, by processing information, it can be combined with other artificial neurons to build the so-called neural networks. So basically, the idea of neural networks is that by building such networks, we can potentially train this artificial network to detect patterns in data. So there's input layers that basically take the input. There are hidden layers that basically are not directly accessible. And at the end, we get an output. In practical terms, basically, you can think of it as, for example, having like 5 different images being processed in some way and being classified at the end, where this is a cat, a dog, or something like that. And the term deep learning basically comes from the fact that we can have multi-layered artificial networks. So having networks that basically have several layers so that we can process the information in several steps. Major frameworks that are used are PyTorch and TensorFlow, developed by prominent companies in the industry. And basically, this is all in a nutshell. We'll go into more details as we go along. But basically, machine learning and deep learning are not all there is about AI. Actually, it is just a subset of AI. And we need to go into the early stages of AI to better understand it. Basically, the idea of artificial intelligence is all just the word itself. There are literary examples of it as theory in antiquity. And probably the biggest leap in artificial intelligence was in the 20th century. The first things were, of course, some form of sci-fi robots, because there were already some machines, and we have some interesting ideas like the positronic brain of Asimov and so on. But basically, the first actual idea about practical implementation of artificial intelligence was Dartmouth College. As any software project, you can see it was very interesting as an idea to have like a 2-month, 10-month study of artificial intelligence. Well, it didn't quite manage to create the core idea of artificial intelligence, to have some kind of intelligence that's similar to the humankind. What happened is that well, we realized that we are quite far away from actually having a complete artificial intelligence, that we should rather start working on smaller tasks that are more manageable. And first, there came some form of expert systems that helped with basic classification tasks. Then there was the concept of machine learning, the ability of having the machine themselves extract useful features that can be learned. And over the last 20 years, we see the rise of deep learning, the usage of deep neural networks, which was predominantly spurred by the much faster hardware that we have at our hands right now. But the problem with AI is that it's still narrow. It is classified as narrow intelligence because it only can work with very small tasks. It's not yet the so-called artificial general intelligence, which is what we have as a equivalent of the human mind. And further down the road is the artificial superintelligence, which is something that surpasses the human mind. And one of the main challenges before AI to get to general intelligence, which is the second step, is basically that the data that we are feeding various kinds of artificial intelligence is somehow limited. It is narrow in scope, and it's somewhat indirect representation of our world. There's no inference about the logic of things and the larger connections in terms of context between different objects. And this is important to remember when we get to the chapter of the metaverse. But for now, it's good just to know that we are still in the early phases of the evolution of narrow artificial intelligence. Okay, so let's see some applications of machine learning in computer graphics. Basically, computer graphics is dealing both with 3D and 2D to some extent graphics, but in a simple term, we use 3D scenes that have specific scene parameters such as size, what is the viewport of the 3D scene, what are the lights and various materials, or the actual way the geometry of the objects looks. It goes through a software program called Renderer that basically generates images. If we delve a bit more into that, basically, typically 3D authoring tools such as 3D Studio Max, Maya, Blender are used to create 3D models that are then rendered by either, for example, game engines such as Unity, 3D and Unreal Engine in real time, or as video through renderers such as Chaos's V-Ray. And in the end, we get either an image or a stream of images or a video. And one of the most common problems with that rendering is that we sometimes get to situations where we have some noise in the images. And this is the first thing that we can use ML to help us with. Basically, when you have a very complex scene with many 3D models, heavy textures and all that, you can have some kind of graininess in the preview when you're viewing the scene and you don't have sufficient time to render enough samples. And NVIDIA have a very interesting technology which helps solve that to some extent. That's based on machine learning. And they have a nice overview of the general idea. Basically, they pre-render thousands of training images and basically train a neural network to detect noise and reconstruct the images in a more clean version. And then use that trained artificial neural network to noisy images to remove that noise. Well, overall, this sounds simple enough, but how does it actually work under the hood? Several years ago, they published a really nice paper which describes that, and it is achieved through a recurrent autoencoder. Well, it's nice to know, but again, how does this actually works? Let's get into more detail. So basically, computer vision is how the computer sees images that we use. We all know that the most popular format for images is through raster graphics, which basically is a grid of pixels within an image. And for each pixel, there's a number value that corresponds to the exact color. And so this is what actually the computer sees, just a bunch of values for the different pixels. Now, let's see how we can use that in a neural network. We know how neural networks work. Basically, we input something and we try to learn some patterns from it and get some kind of an output. So basically, can we just take the images and put it in some kind of a array and just feed it into the neural network? Well, we could do that, but it wouldn't be very easy for the network to infer some kind of a pattern, because it's just like a huge array of numbers that makes no sense. It would be much better if there's some form of a scanner that goes through the images and looks for features, but tries to analyze several pixels at a time, not just one, but several, and see if there's some kind of a pattern, some kind of a feature that can be seen there among those several pixels. And actually, this is what convolutional neural networks actually do. So they take input some kind of image and go through several steps that are pretty much similar. Basically, there is a convolution operation and pooling, convolution operation, pooling. At the very end, there is some kind of a task that can be done from the resulting features. So it can be a classification, but it can be all sorts of stuff. Here, we get that pipeline, but basically the idea of that pipeline of similar steps is to build a hierarchy of features. So basically, we can start with some kind of a low level of features such as edges, dark spots. Then we get to a higher degree of features like eyes, ears, nose, and at the end we get some kind of a higher level feature. And as we can see in this illustration, basically by going through these steps, we can gradually find some higher level features that can be useful for our needs. And let's get into a bit more detail about the actual convolution and pooling operations. Basically, the convolution is progressively scanning the image. By using the so-called filter, it can be also thought of as kernel that progressively just scans the image in steps that are called strides. And by scanning the different separate pixels, it can very quickly decide if there's a specific feature. So when the filter goes through the different sections, it basically does element-wise multiply for each of the pixels and defines the output. Here, this is a grayscale image, but for colored images, we can have just the same, but with 3 different filters for the 3 main channels. And basically calculate for each pixel, each group of pixels, the potential occurrence of a specific feature. The pooling operation is also sometimes referred to as downsampling, but basically this is what it does. It compresses the image to some extent. This both decreases the computational power that's needed to process the data, and at the same time it helps extracting dominant features, because you don't want to have patterns that are so precise to a specific image, because that kind of learning won't be really useful. You want to extract real features that are potentially occurring in multiple different images. There are different types of pooling. You can have like max pooling that basically takes the biggest value from a group of pixels. You can have average pooling that basically takes the average of the group. It really depends on the types of images that you want to process. Sometimes, most often, max pooling is used, but sometimes average pooling can be used. We see things here just as numbers, but if you imagine, for example, various images, if you have like high contrast image, you might want to tweak some numbers because you have a very large number for one pixel and a very small number for another. And if we put all together, we can see a very simple model defined in TensorFlow about what we discussed as 2 main operations. We have convolution with specific filter size. We have activation function, which we discussed in the beginning, is what adds nonlinearity to the neural network. We have max pooling with size and strides, and basically in a couple of steps, we get to some kind of a more dense representation of the feature, and at the very end, we can potentially classify. So going back to our recurrent autoencoder, we have the first part. Basically, we have, as we can see, the convolutional network that we can use to potentially extract some features. But there are a couple of other items that are somewhat missing. So the next one is autoencoders. Basically, this is something that is the inverse to some extent of a convolutional network. It's deconvolution as an operation and basically upscales the image so that basically we get to a larger version of it. And by measuring the output reconstructed image at the end towards the initial image, we can define the loss and potentially train the network to automatically reconstruct better and better ideal copies of its input. Here we have another example that's in TensorFlow about autoencoder. We can see it's very simple. Basically, we have convolution from an input. We don't even have pooling here because, as we can see, it's very small, 28 by 28 pixels. But basically, we have a couple of operations with convolutions, and then deconvolution or convolution transpose that inverses the process and creates upscaled copy of the original input. And we have the second part. So we have convolutional networks to extract the features. We have autoencoder to automatically reconstruct the input. And we have just one last item for our recurrent autoencoder. And this is recurrent neural networks. What is special about them is that they do have state or memory. Typical neural networks, they just take information and output it, but they don't store anything. And recurrent neural networks can do that, which is to some extent problematic because it can slow down some operations, but at the same time, it's very useful when you have to provide some kind of sequences of information. And it's very often used for natural languages processing, which is something that is used to process basically speech and text, because as you know, in natural languages, you don't want just one word or or a couple of words, but you want to have some kind of a meaningful structure within a sentence. So they're very useful for that. They have simple implementation built in TensorFlow, very easy to use. And basically, these are the three components of the recurrent autoencoder. We have convolutional network to extract the features. We have autoencoder to basically reconstruct the initial image. And we have a recurrent network to process image sequences. So because specifically for OptiCX, the technology of NVIDIA, they want to use several rendered images that are rendered in sequence, because often you have sequences of images, not just one. And there's some useful information that you can get from previous images that you can reuse potentially in new ones. Very similar approach is used again by NVIDIA for their DLSS technology that's mostly used for real-time rendering for gaming. This is deep learning supersampling. They again train a convolutional autoencoder to create images by basically having much better copies rendered in a separate machine, and by upscaling the image to, for example, 4K, they can compare the ground truths to the rendered image and potentially train the network to produce better and better copies of itself. It really improves frame rates, especially for large resolutions such as 4K. So it's really an awesome technology. What is a bit more different here is that they even have additional information that comes from the game engine. such as motion vectors, which basically informs the neural networks the possible position where some objects will move, so that it can better infer what would be the predicted rendered image. And the cool thing about these technologies is that they're basically evolving. More and more render samples are done, and basically this helps to the network to be actual recurrent autoencoder to be better at generating new and newer, more high quality samples. And we can see here difference between version 2.1 and 2.3 in popular game Cyberpunk. And this is something that happens much faster than traditional upsampling algorithms that are manually crafted by people. This is something that the machine can learn from itself every day, constantly, 24 hours a day. And as much as improving the image quality is really nice for image denoising and for upscaling, we can use machine learning not only to improve the quality, but to generate some content. And this happens in a way that is very actually simple, at least on theory. The idea is that we already have the autoencoder and infrastructure, and we have one network that basically is extracting features and another that's trying to reconstruct better copies. What if we decouple the two networks and make it so that one network is just generating some kind of a image based on variations such that are inputted as noise, and the other network just needs to find if the generated content is good enough. These are exactly the so-called generative adversarial networks. There are two neural networks that basically compete with each other. There's one that's called the generator that basically turns noise into imitation of data to try to trick the discriminator, trying to provide fake images. And the discriminator is fed both with real images and with fake ones from the generator. And the goal is to make the generator better by constantly trying to train it to produce better copies that are closer to the real, so that the discriminator is tricked. And these GANs have very cool applications. Basically, one of the most popular ones is the so-called style GAN. It was originally developed by NVIDIA, but it's now source available. As you can see, all the portraits that you see here are not real people. These are generated on the fly, and you can try it yourself. There is a site that's called thispersondoesnotexist.com. Basically, you can go there, and each time you load the page, you get a different person, and if you reload it, you get a different person. So it's really amazing how photorealistic these generated persons are. Another cool example is CycleGAN. Basically, with it, we get style transfer, so you can have like an artist style of a standard photo, or you can have zebras that look like horses and horses that look like zebras, or you can have landscape changes like summer, winter for a photo. So it's really cool to see. Another example of NVIDIA that they have in their AI playground is GauGAN. That's basically you can draw some parts of imaginary landscape, and it generates all sorts of content for it. And another very interesting application is GameGAN. So basically, this is a GAN network that recreated the famous Pac-Man game just by watching videos of the game, which is kind of amazing because typically in a game engine, you have a ton of different people that are actually creating the game. You have programmers, you have artists that create the artwork, there are game designers, there's the actual game engine. But here we just have neural networks that watched the game and recreated it. And it was for the 30th anniversary of the original Pac-Man. And it was really cool, invention. And it's not only that, but people at NVIDIA are looking to get to the next step of things, 3D. So there's already some research going on in the field of inferring information about scenes from actual 3D scenes. So we can see here a more advanced version of GameGun that basically creates some kind of a basic racing game. And on the right-hand side, we can see Metasym, which basically is trying to synthesize whole scenes, because this is how actually games are organized. Basically, you have trees of different connected assets, and it's really interesting to see how far they've come. Of course, when we get to the field of trying to understand things from 3D, we get to another topic that's now called differentiable rendering. So what is it? Basically, if you go back to the original topic of rendering, we know that we have a collection of assets organized in a scene that basically has some materials, scenes, cameras, all that's being rendered to produce the image. And the differentiable rendering goes the other way around. So basically, it gets an image and it tries to potentially infer from it all the various properties, 3D properties of the objects in real life. So basically, having a combination of inferring information from about the scene and at the same time rendering it. And by comparing at the very end what is being rendered, it can potentially evaluate the loss and potentially improve itself, because at the start of the network it will probably create images that are very ugly and far away from what is needed. But as it continuously tries to learn different objects in the scene and tries to build 3D models from them and feed them through a renderer and render them and compare it, they can in time produce much better results. We can see here an example from the differentiable renderer in the Kaolin library that's available from NVIDIA, that basically shows some results on that. Basically, we have just an input basic image of actual bird, and based on it, just on it, it predicts the actual shape, the geometry that's building the 3D model. It can predict the texture or the actual colors that will be applied to a 3D mesh, and at the end provide some kind of 3D model. Although it's obviously not perfect, it's after all just automatic 3D model from just one image, which is really amazing. And if we go a bit more into detail how this happens, basically they have several networks combined to achieve that. They first have StyleGun that basically generates some variations of cars. This specifically for image to car library that's available from NVIDIA, and they use that to have it as a sample data for the inverse graphics network. That network basically goes again through a series of convolutional layers to define three main components of the 3D models: the mesh, the actual geometry, the lighting, and the texture, the colors. So That is then fed to a renderer that basically renders the actual inferred 3D object. And then all that is being compared to the original reference. And in that way, progressively, through differentiable rendering, more 3D objects can be created pretty much automatically. And Kaolin is PyTorch library, but available from NVIDIA, but they're pretty much all the major libraries and frameworks that deal with deep learning have some implementation already for differentiable rendering. And it is a very useful feature if you want to create progressively better and better 3D assets in an unsupervised fashion. And we get to the last section, the asterisk verse and the final destination of AI. I'll tell you in a bit why this is considered by some people the final destination of AI. But first, what is the multiverse, the omniverse, and different verses? These are just virtual worlds. So a world where in some way people can collaborate, play, and do all sorts of stuff. Facebook, now Meta, goes more into the social-like aspect of it. Place where you can talk with people in virtual environments with virtual headsets and all that. Epic Games is more into the gaming side of things. So we can see here Fortnite, a virtual event for preview of Star Wars. So one another application. NVIDIA is going in multiple ways, but their version of the multiverse is called Omniverse, and it is used for a variety of applications, such as, for example, training of self-driving cars that, for all intents and purposes, are essentially robots. And they put basically the sensors of the car, put information from 3D world inside of the sensor of the car so that they can use it to train it. And because their rendering is so photorealistic, the car cannot really tell if it's being driven in a real world or it is in the omniverse. So it's very useful for them to train these self-driving cars in a much faster way. And apart from that, they have also all sorts of different cool applications for AI, so such as virtual assistants, virtual avatars. There is a library called Audio to Face that basically takes audio inputs and generates facial animation. So this is quite useful when you want to, for example, have animations for different languages, or you just want to have an avatar that essentially speaks. The Omniverse is nicely integrated with Kaolin, so you can basically interactively see how the models are trained and how differentiable rendering, for example, is improving the quality gradually. And what's even cooler probably for Omniverse is that they're supporting a new format called USD that basically is meant to be somewhat of a HTML for the 3D. So basically, in a simple declarative matter, you can define 3D scenes in a universal format that can be very easily processed. And at the end, what does this actually mean? Basically, it is something that allows AI to learn in a much faster way, because if we, for example, very quickly look at how it actually works in the current setup, basically, if you want to shoot a picture of an apple, it goes through a ton of different things. So basically, a lens, then you have masks, and then you have image sensor, and then you have saving of files, and then it goes through convolutional network, and maybe after tens of thousands of training sets from images from Apple, you get some kind of a classification with good percentage of accuracy that this is an apple. And with USD and the Omniverse, you can have much better and easier understanding of the actual object. So basically, the images of the real world are just 2D representation of 3D objects. And data defined as computer graphic scenes and assets can be much easier to process by ML. And the verse presents pretty large amounts of structured, persistently available data that potentially can be the thing that AI needs to get to a much higher state than its narrow applications right now. Well, we'll see what happens. Of course, there are a couple of types of people, but some believe that AI will practically destroy us. Some believe that we're too far away and there's nothing scary, but I guess time will tell. A few quick takeaways before we wrap up. AI still is in infancy. It's a long way from its ultimate goal, super intelligence. Modern deep learning is based on networks of artificial neurons that looks for patterns in data. There are many types of networks depending on the needed case, but they're modular. They can be combined to get the desired result. And convolutional networks are pretty much at the core of all vision, image related tasks. At the very end, we saw that the inverse is a unique opportunity for computer graphics to be used as a base for new and faster way to learn. I sincerely hope you learned something new. There are some references also, and don't forget to visit our virtual booth. And thank you all. And now I'll take your questions.
Така. Благодаря ти за интересната презентация. Видях някои много вълнуващи неща и някои много опасни. В смисъл, че така сетих се за няколко начина, по които вече човек с въображение би могъл да направи една фалшива новина да изглежда още по-реалистична и още по-трудно да я разграничим. И докато да дадем някакво време на останалите да дадат някакви смислени въпроси, аз бих искал така да реша един мой личен проблем, защото ти знаеш, когато си хост на конференция, най-удобното време да решаваш личните си проблеми. Въпросът е, че аз съм с много опит, също така съм и много скромен по принцип, но това го знаят моите приятели и познати и те така често ме използват да им преинсталирам Windows. И за други консултации, разбира се. И се притеснявам много, че аз познавам човек, който познава друг, който познава трети и така нататък. Някъде, може би, по веригата 1000 дни ще познава Джеймс Камерън. А пък той от 12 години се мъчи да направи Аватар 2. И се опасявам, че по някое време той ще си попита познатия, който ще попита втори, трети, пети, и накрая ще стигне до мен да ме попита какъв лаптоп да си купи, за да може да рендира такива реалистични изображения, нали, за да може все пак да направи Avatar 2. Нещо да ни кажеш за инфраструктурата, която човек трябва с която човек трябва да разполага, за да може тези неща, които ги показваш, всъщност да се случват.
Да, разбира се. Нали, не искаме да залагаме на конкретни кампании да изглежда като реклама, но истината е, че NVIDIA, за сравнение с прямо ATI, имат доста по-голям чисто стратегически интерес да развиват AI, докато нали, AMD, ATI, те по-скоро имат други приоритети, така че човек, ако си купува нов хардвер, в момента иска да се занимава с конкретно компютърна графика и machine learning, би ги посъветвал да си вземат NVIDIA, защото те същевременно и софтуер, и хардвер много силно разработват и би било по-логичният избор в момента, чисто обективно на база количеството неща. Примерно това, което видяхме за Deep Learning Super Sampling, то изобщо не съществува, нали, за карта на AMD. Те разчитат на определен обикновен тип upsampling, който не използва изкуствен интелект. И това би било моята препоръка. NVIDIA, поне към момента. Нали, знаем, че нещата се променят.
Въпрос на видеокарта просто.
Основно е по-скоро въпрос на човек и колко му се занимава, но Нали, ако някой човек по-скоро в момента се чуди какъв хардвер да си вземе, бих го насочил към NVIDIA, но въпреки това, нали, голяма част от нещата са достъпни нали, и за, така да кажем, агностично от GPU. Нали, голяма част все пак от нещата, нали, които са особено така за начинаещи, са нали, дори доста по-скромни като изисквания спрямо съвременните компютри, така че не е фатално, но най-добре е просто с NVIDIA.
Добре, успокоиме доста до някъде да ти кажа.
Да, за Джеймс Камера се притеснявам.
Да. Аз от 12 години се притеснявам за него и просто си мислех, че трябва човек да притежава стая с хардуер, която да може с която да може да рендира анимация, която да е достатъчно реалистична.
Ами да, това е интересна тема като цяло, която по принцип може да се направи една цяла дискусия около това нещо, но така всъщност NVIDIA доста се развиват от към гледна точка на cloud технологии, нали, съответно доста по-мощни суперкомпютри, които могат или да рендерират доста по-бързо, или също времено да се използва за трениране на невронни мрежи. Така че и това е една друга посока, която те доста така чинно следват. Да,
добре, окей. Ами, виждам, че нямаме въпроси от присъстващите на конференцията. Благодаря ти много за участието. Беше супер интересно. Пожелавам ти всичко